In the last lecture we looked at a vector in two-dimensional space, and we saw that if we wanted to reconstruct it from its components, then in a general coordinate system, which may not be orthogonal, then we really had to be careful about how we defined, how we orient our torch to project a shadow onto the axis. And we saw that there was only one orientation of the torch that was correct, and that was the one that gave us the superscript components, so the A superscript 1 and the A superscript 2. But what we've taken for granted so far is that there are basis vectors, which we called E1 and E2. So in this lecture we'll consider basis vectors in more detail. We'll talk about how basis vectors can transform between different coordinate systems. And we'll also look at the corresponding description of the components of the vectors. Okay, so we saw in the last lecture how the contravariant components, so the superscript components, went with the basis vectors. And we'll develop these ideas further here. In the previous videos we've drawn basis vectors on our coordinate axes, but we haven't actually talked about these basis vectors at all. So that's what we're going to do now. So this is talking about natural basis vectors. Okay, so we've got some coordinate system with n coordinates, x1, let's have an xi up to xn. And let's think about a point in our n-dimensional space. So let's have an origin O. We've got a point that's at some vector r. So this is a vector in n-dimensional space. Now let's think about moving from this point r by an infinitesimal amount in a way that we vary just a single one of these coordinates. And let's choose the ith coordinate to vary. Okay, so let's vary our xi. Okay, so we move to a new point, r plus dr. And this vector that joins the 2 points, dr, it's tangential to the coordinate curve at this point r. Okay, so what's the coordinate curve? It's the curve traced out by varying just one of these coordinates whilst keeping all others constant. So maybe the coordinate curve for the ith coordinate looks like this. Okay, badly drawn, but this is tangential to this curve. Okay, so let me fix this up. Okay, so this is the coordinate curve for xi. Okay, so what is this dr? Well, we know from the chain rule that dr is equal to the partial derivative of r with respect to each of the coordinates. So let me put 1 dx1 plus dr by dxi up to dr by dxn dxn. Okay, so if we only vary one of the coordinates, then dx1 is 0. Okay, so this term is 0. All the other terms are 0. dxn is 0. And the only one that survives, of course, is this dxi term. Okay, because we're varying the xi. So in this case, our dr equals dr by dxi dxi. Okay, and at this point it's important because we now have a repeated index, and this in this case is not signifying a summation. Okay, so here we have to be careful, we have to write no summation. Okay, this is a single term only involving the ith coordinate. Okay, so this dr is equal to, let's just rearrange this, dxi dr by dxi xi. And we call this guy the natural basis vector for coordinate xi. And we call this E. It's a vector. And we give it a subscript I. So dr, this vector, is equal to dxi ei. So this is a component, and this is our natural basis vector. So ei is defined by dr by dxi, is called our natural basis vector. Okay, and these natural basis vectors are what we were drawing before without much thought. So we were looking at our xy axis. Our natural basis vector is tangential to the coordinate curve. So we were drawing an E1 for the x and an E2 for the y. Okay. Okay, so now let's consider not just varying xi, but let's vary the coordinates all at once. So let me just rub out and we'll restart. So now let's think about moving from r to dr in any direction. And our dr is just given by the chain rule again. It's dr by dx1 plus, and let's have dr by dxi dxi. This is an r, plus dr by dxn dxn. Okay, so here we now have the summation restored. We can just write dr by dxi dxi. Okay, and this is the summation restored. So because we have a repeated index, this means that there is a summation over all the i's. Okay, there's a sum over I from I equals 1 to n. Okay, this is our Einstein summation notation. And we knew that, or we found out that these are called our basis vectors, E, I. So in the general case, we have dr equals dxi, and then the basis vector ei. Okay, and this is our component. So this is a vector, dr. This is a component, and this is our natural basis vector. And you'll note that the component, we use a superscript. This is a contravariant component. Okay, and we learned about those in the last video. This is when we shine our torch parallel to the opposite axis. Okay, so we can reconstruct our vector using the contravariant component with a natural basis vector. Okay, and we'll see that the covariant components that we saw we couldn't reconstruct our vector with, we'll find that we can't reconstruct our vector with a covariant component and a natural basis vector. But just as the contravariant component goes with the natural basis vector, a covariant component goes with a different type of basis vector. Okay, and that's what we'll look at in the next video. Okay, but for now we'll stick with these contravariant components and natural basis vectors, and we'll see how they transform between coordinate systems. Before we move to looking at transformations, let's look at an example. So if we think about a two-dimensional coordinate system, x and y, and let's have some vector r. Then this vector r is at, okay, we'll have unit vectors I hat in the x direction and a unit vector j hat in the y direction. Then this vector r is at x I hat plus y j hat. Okay, so the coordinate of this point is at x, y. Now let's think about a polar coordinate system. So let's have the same vector r. And now it will be r cosine some angle, which is theta. So that's the component in the x direction, times I, plus r sine theta in the y direction, times j hat, unit vector. Okay, so our natural basis vector EI is defined by dr by dxi. So let's work out what this is in each case. So here our x1 is x and our x2 is y. So our E1, which we can call it EX, it's equal to the partial derivative of this thing with respect to the x coordinate, dx, keeping the other coordinates constant. So we keep y constant and vary x, then this just gives us the differential of x I hat vector, which is just 1 times the unit vector. Okay, and similarly for the second coordinate, which is y, our natural basis vector in the y direction, we call it EY, it's dr by dx2, which is y. Okay, and it's no surprise this gives us the j hat. Okay, as you expect. Okay, these are our natural basis vectors in the x and y directions. Okay, and we can think about a unit vector r in the r direction and a unit vector theta hat in the theta direction at this point. So let's think about what our natural basis vectors are. So our E1, which in this case is E subscript r, and it's dr by d scalar r. Okay, so our first coordinate is r. So this is dr by dx1, and our x1 is r. So dr by d scalar r is just cosine theta I hat plus sine theta j hat. And this is just the unit vector r hat. Okay, as you know. If we think about our theta, so this is our second natural basis vector in the r theta coordinate system, then we can call this E theta. And this is dr by d theta. And this is, so r cosine theta, partial derivative with respect to theta, is minus r sine theta, I hat. And then r sine theta, j hat, partial derivative with respect to theta, is just r cosine theta, j hat. And we can write this as r theta hat. Okay, where theta hat is minus sine theta I plus cosine theta j hat. That's this vector here. So we find that our first basis vector E1, which is ER, is equal to r hat. But our second natural basis vector, e theta, is not a unit vector, it's r times a unit vector. Okay, so this demonstrates that our natural basis vectors don't have to be unit vectors. In the Cartesian system, we find that they are. So E1, this is EX, equals I, it is a unit vector, and EY equals J hat, it is a unit vector. Okay, but in general, they don't have to be unit vectors. Okay, they don't even have to be orthogonal. Now let's think what happens when we transform between one coordinate system, so x1 to xn unbarred, and we transform between that and a different coordinate system, x bar 1 to x bar n. Okay, so they're both n-dimensional spaces, but we've picked two different coordinate systems. So we've seen that our natural basis vectors in our unbarred system are called E sub I, and they're vectors, and they are partial derivatives of some vector r, and this vector r lives independently of the coordinate system with respect to the coordinates. So you'll see that once we choose a coordinate system, we naturally have a set of basis vectors that go with it. If we choose a different coordinate system, then we have a different set of basis vectors, ei bar. Okay, they're vectors, so they have an arrow. And these are dr by dx bar I. Okay, so this is a vector. It's the same as this. It's a vector that lives independently of any coordinate system. But in each case, we've chosen a coordinate system, and thus we've chosen a natural set of basis vectors. And the question is, how are EI and EI bar related? So how can we express EI in terms of EI bar? Oops. So we've got question marks here. Okay, and it's quite straightforward. We just have to invoke the chain rule. So let's work on the left-hand side. And we can have E sub I is equal to dr by dxi. And using the chain rule, we can write this as dr by dx bar, so the barred coordinate j, dx bar j by the dxi. So this thing we can see is just exactly E j bar. So this is E j bar. So we find that our natural basis vector in the unbarred system is given by E j bar dx bar j by dxi. And this thing is just an element of our Jacobian matrix J bar. If we do the inverse, okay, then it's the same procedure. We think about EI bar in terms of EI. So this is just expanding this as dr. So this is now EJ, and we have an element of the matrix dxj by dx bar I. And this matrix element is just the matrix element of the Jacobian matrix J. Let's think about a general vector T. We're not going to think about the components and how the components transform between the coordinate systems. So we know that for our vector T, we can write this as a sum of components ti and basis vectors ei. Okay, and we've seen an example where we constructed a vector by going some component along some coordinate axis plus some component along a different axis, and that's just what you've been used to from school days in terms of constructing a vector. So I hope you're happy with this. And there's a repeated index here, so again that means we sum from 1 to n. Okay, so this expression is a summation including t1, e1 plus t2, e2, etc. up to n. Hopefully you're happy with that now too. Okay, now we could choose an alternative coordinate system, this x bar one, and in that system we have a different set of components called ti bar and a different set of basis vectors called ei bar. And the important point is that our vector t is independent. It exists independently of any coordinate system. Okay, so that's why we can write this. And also, you should realize that no coordinate system is superior to any other. So the question is, how do t and ti bar connect with each other? So how can we go from ti bar to t and vice versa? So what happens to the components when we transform between coordinate systems? Okay, so we'll use the fact that t is invariant. Okay, t is a vector that exists independently of our coordinate system, I should say. So let's just work on the left-hand side. So let's write ti ei. Okay, and let's use what we know about the natural basis vectors. They transform, as we've just seen, as ti. So this ei is equal to ej bar dxj by dxi, and this has got a, yes, let me think, it's an inverse Jacobian matrix. Okay, so that's the left-hand side, that's this thing. Now let's think about what this is. We can just write this as equal to ti bar e bar I, like this, okay? Now this I is a repeated index, so we can be a bit more clever and relabel this. Not I, let's call it j. Okay, and then we can see that on the left-hand side, this thing, we have ej bar multiplied by something, and something involves this term and this term. And here we have ej bar also multiplied by something. Okay, so this something is the tj bar. tj bar equals, and we know what it equals now. It equals ti times a Jacobian matrix element dx bar j by dxi. Okay, and this is a very important relationship. And this is our definition of a contravariant vector. Okay, and when we say contravariant vector, we really mean the components of the contravariant vector. Okay, but you'll see that this is used as loose terminology. Okay, so we really mean the components of. So we mean the components of the vector. Okay, so a contravariant vector is a set of n functions that transform between coordinates as given here, where this matrix is the matrix element of our Jacobian matrix J bar. Okay, so in our more concise notation, this is Tj equals ti d I x bar j. Okay, and these are elements of our Jacobian matrix J bar. So to summarize, we found that the coordinates transform in the following way. So t, let's call it I bar, equals dx by dx, and there's a bar on the top, and there's a t here, and let's call this j. And then we have to think about what's I and what's j. So we sum over j, and I appears on the top, so it must be I here and it must be j here. Okay, and also that our basis vectors ei bar equal dx by dx, and now there's a bar on the bottom. We have ei unbarred. Sorry, ej. Okay, and we've got to have an I on the bottom, so this is the I, and we have a repeated index to sum over j. So that's how it goes. So if we put these two together and look at this equation, then we should see that this holds true. So if we consider ti times ei, ti bar times ei bar, this equals, so ti bar is this thing, it's dx bar I by dx, let's call this a, dxa ta, and ei bar is dx b by dx bar I. Okay, so I is the coordinate that must stay as I, because this is E sub I. And then we have an E B bar. Okay, so this equals dx bar I by dxa, dxb by dx bar I, ta E vector b. Okay, so we've got a dx bar I and a dx bar I on top and bottom here. So this is equal to dxb by dxa. Okay, so this is just a chain rule. And this is taeb. But our coordinates are independent, so dxb by dxa just give us a delta AB, or BA, whatever. TAEB, and this equals TAEA. Okay, and this is a repeated index, so we don't have to call it A. We can call it anything we like. So let's call it I. So we've shown that TIEI bar equals TIEI. So this thing holds true, as we expect. And the point is that these relationships, you can see that they act opposite to each other. So this involves the matrix J bar, and this involves the matrix element of J. And remember, J and J bar are inverses. So this equals J to the minus 1. So our vector t exists independently of any coordinate system. So if we express it in this representation using the unbarred coordinate system, and we transform coordinates, then whatever happens to the components ti, the opposite must happen to the basis vectors ei, so that the overall vector remains unchanged. And this is just what we see. The components transform according to the J-bar, and the basis vectors transform in the opposite manner using the matrix J. So these are key equations that describe the contravariant components of a vector and the natural basis vectors and how they transform between two different coordinate systems. And we'll see that we just generalize these to define tensors. So we're close to defining tensors, but we first need to think about the other components of our vector, the covariant components, and the basis vectors that are associated with it. And at this point I should say that previous lectures of the module started, okay, and I mean started, almost the first thing they wrote down was that this is the definition of a contravariant vector. Okay, so I hope you've appreciated a slightly more gentle introduction, and I hope that the previous videos and notes have been useful to gain some intuition. I appreciate there's a lot of indices going on and things look maybe more complicated than they actually are, but so far all we've done is effectively use the chain rule, and you'll become very familiar with these types of expressions. Okay, so it doesn't get much harder than this, we just see this repeated lots and lots. So you will be familiar, so don't be too intimidated at the moment. It will become second nature. Okay.